I'm Yunli from Tsinghua University. Today I'm going to present our work, Efficient Three-Party Computation for Binary Circuits with Application to Maliciously Secure DNA Inference. It is a joint work with Ant Group and Alibaba Group. In this work, we focus on three-party computation where the function is expressed by a binary circuit. We consider a malicious adversary who controls an honest majority of corrupted parties, and assume that the communication network is authenticated, secure, and synchronized. One of the state-of-the-art works in this line of research is the one based on cut and choose and beaver triples. This approach has low computational cost, but incurs high communication cost. In the work of FLNW17, each party needs to communicate 9 bits per AND gate. And the follow-up work, ABFL plus 17, also needs to communicate 7 bits per AND gate per party. Another representative work is BJ19. It uses distributed zero-knowledge proofs to achieve sublinear communication costs in the verification phase. And thus, the amortized communication cost of BJ19 is the same as the semi-honest protocol, only 1 bit per AND gate per party. But it relies on binary extension fields to perform distributed zero-knowledge proofs, and thus incurs high computational cost. So this naturally leads to a question. Can we achieve the same communication complexity as BJ19 and also a comparable concrete efficiency as FLNW17 or ABFL plus 17? Our result is yes. We built a maliciously secure three-party computation for binary circuits. It has the same amortized communication complexity as BJ19, as well as a comparable computational overhead with FLNW17. We also apply our protocol to secure DNA inference and test it on 3 DNA models. Now we are going to introduce our techniques. Before that, let's first review our starting point. We found that the key to achieving sublinear communication costs is the distributed zero-knowledge proofs used in BJ19. So let's first review the BJ19 protocol. In BJ19, the parties use replicated circuit sharing to compute the binary circuit. Now assume that they wish to compute an AND gate, Z equals x dot y. Each party Pi holds replicated circuit sharing of inputs x and y, and also two randomness ρ I and ρ I-1 for random masking. Using these shares, each party Pi can compute an additive share of Z, denoted by Zi, and then passes around Zi to the next party. And now the parties hold a replicated circuit sharing of Z. After computing all AND gates and before reconstruction, the parties need to verify the correctness of all AND gates. Each party Pi has to in turn act as a prover to show that Zi is correctly computed. The other two parties will act as verifiers and check the proofs together. Here we can note that all the provers' data is distributed between the two verifiers, and thus they can utilize distributed zero-knowledge proofs to perform the check. But for binary circuits, they have to lift the computation over the binary field up to its extension field, and apply the distributed zero-knowledge proofs over the extension field. This is quite expensive. On the other hand, previous works has experimentally shown that distributed zero-knowledge proofs over prime fields have good efficiency. Thus, our idea is to do verification over a prime field rather than a binary extension field, and take advantage of the algebraic structure of prime fields to further reduce the computational cost. We first show the basic construction of our verification protocol. Our first step is to simplify the equation we want to verify. Assume that P1 is the prover. We rename these variables and divide them into 2 groups. The first group, A, C, E, are all variables known by the prover P1 and the verifier P2. The other group, B, D, F are all the variables known by the prover P1 and the verifier P3. Note that here we define a new variable E by merging some intermediate results together. This is helpful for reducing the degree of the following up equations. So after this step, we can get a simplified equation expressed by A, C, E, and B, D, F. Now we are going to transform the equation from the binary field to a prime field. Here, a key formula we utilize is for any two bits alpha and beta, alpha XOR beta equals to alpha plus beta minus 2 times alpha times beta mod P, which can be further expressed as alpha times 1 minus 2 times beta plus beta mod P. Here, P is a prime number. Using this formula, we can transform the equation from the binary field to a prime field. Next, we simplify the transformed equation again by merging intermediate results together, and define new variables G1 to G4, which are known by P1 and P2, and H1 to H4, which are known by P1 and P3. After this step, we can get an inner product relation over the prime field. Now we want to bench verify in multiple AND gates. In BJ19, this requires a random linear combination, but here we don't need it. Note that if any AND triple is incorrect, then the corresponding inner product relation will equal to 1 instead of 0. So we only need to add up the relations directly and check whether the final result is 0 or not. As long as the number of AND triples M is less than P, then the summarized result equals to 0 if and only if each single relation equals to 0, which means that all the AND triples are correct. So here we don't need any random linear combination. So far, all the computations can be done locally by the parties without any interactions. And after this step, the parties can utilize the distributed zero-knot proofs over the prime field to check the benched relation. Actually, here we can further improve our efficiency. Now we show one of our key optimizations. As said before, we don't need random linear combinations for bench verification. However, we found that if we use specific coefficients for linear combination, we can achieve further speedup. More specifically, we can choose the powers of 2 as coefficients for linear combination. This enables us to use native CPU computations for bench computing prime field data directly from the binary data. It can greatly reduce the computational cost. But here we have to ensure that when all the triples are incorrect, the result of the linear combination won't overflow P. So we can choose the 61-bit Mersenne prime, and it is sufficient for any circuit size less than 2 to the power of 33. We also have other optimization techniques, such as we use lookup tables for polynomial evaluation, and we use Mersenne fields for fast arithmetic computation. We also use fast inner product operations over fields for further speedup. Please check our paper for more details. We evaluate our protocol and compare it with BJ19 and FLNW17 using the MP-Speeds framework. Here we choose FLNW17 rather than APFL plus 17 for comparison because FLNW17 is faster in MP-Speeds. Compared with BJ19, we can see from the results that our protocol has almost the same communication cost as BJ19, and we are more than 3 times faster than BJ19 in line. Compared with FLNW17, we can save 9 times communication cost, and we are only a little bit slower than FLNW17 in line, but we are up to 4 times faster in wine. For secure DNA inference, we combine the protocols for binary circuits with MP-Speeds, which is one of the state-of-the-art maliciously secure protocols for arithmetic circuits over rings in MP-Speeds. We measure the time cost for achieving malicious security for the binary part, and it shows that our cost is only 15 to 33% of BJ19 inline and only 7 to 10% of FMW17 in 1. Additionally, we also found a hidden security issue in many of the current probabilistic truncation protocols. This arises from the use of randomness. In this kind of truncation protocols, the same randomness is used for both protecting the privacy of the secret value as well as sampling the 1-bit rounding error. This is problematic when considering the joint distribution of the cooperative parties' view and the protocol output. This security issue is first introduced by Cheng and then used by many of the following up works. As a result, we may have to use exact truncation protocols rather than probabilistic ones, and this will incur more binary gates in secure DNA inference, and thus increases the need of speeding up MPC protocols over binary fields. That's all. Thank you very much.